Okay, so hey, thank you everybody for joining today's webinar. So today's topic is on Apache Iceberg, and we're gonna focus a lot on query performance, all of the things that affects Apache Iceberg's query performance, and how to run them faster. Okay, so let's first take a look at the agenda. So yeah, so if you have a question, please just post them in the Q&A section or just in the chat. We're going to address them at the end. So this presentation, I say, will be like 35 minutes, and then we'll do all of the questions. We'll have time. So yeah, so first we're going to talk about how slow queries can break Apache Iceberg promises, Lakehouse promise, right? Why do we need fast performance? And how fast performance just not just like faster queries or low latency, right? It actually affects your data governance and your whole data pipeline, right? And then we're going to talk about some of the solutions to the problem. So first we're going to go over v3 features, actually one v3 feature that really going to significantly improve your query performance. We'll take a look at how v2 and v1 doesn't work, right? And how v3 addresses that problem. Not only make your queries faster in those scenarios, but also to lower your maintenance overhead, right? To not only increase your your read performance, but also your write performance as well, right? And then we're gonna talk about some common Apache Iceberg performance tuning tips and best practices for analytical workloads, right? And then we're gonna talk about the work that has been done, last year, last few years on the query engine side, how to accelerate performance. And then we're going to take a look at a few um, case studies, right? Leading Apache Iceberg and StarRocks Lakehouse architecture, from industry leaders. So first, let's get started. So same old Apache Iceberg, right? Apache Iceberg is a huge step up from Apache Hive, right? They added a lot of data warehouse like features, like transaction properties like schema evolution, right? Like time travel, like SQL support, right? To data lakes. So why are we doing that? Why are we trying to run data warehouse like workloads on Parquet files, on open and standardized storage and table formats, right? The reason we try to do that is because we want to unify all kinds of workloads on a single source of truth data, right? Just think about if you're using something that's proprietary, right? With the data written in a proprietary format that's enforced by the whole system, right? The number of workload you can run on that piece of proprietary data is limited to whatever the engine, right, that data warehouse supports, right? But running everything on open formats, you can run all kinds of workloads, on that piece of data, right? So you only have to maintain one copy of the data. So it's really great for your data governance. It's really good for your architecture. It really simplify your architecture, and it's overall just very cost effective, right? But once data is in Apache Iceberg, it never leaves, right? Actually, in our experience, no, right? The reality is, queries are just not running fast enough, right? Still, users are still copying their data out of their Iceberg Lakehouse for query acceleration purposes, right? Existing query engines are just not built for this, kind of data warehouse like workloads. They're not able to handle, those demanding workloads such as, customer facing analytics, right? Low latency, high concurrency like workloads, or is caused by just poorly maintained, iceberg tables, right? We're going to talk about how to solve them and using the wrong features and using the features that there, but just not knowing the feature is there, right? So in the end, user over engineer or overspend existing query engines to barely get passable performance, right? But this is really not that sustainable, right? So as a workaround, users are basically forced to move their workloads and their data to a high performance data warehouse just for query acceleration reasons, right? And this is sometimes, yeah, most of the time it does solve the performance challenges, right? Does get that performance SLA. But you have to think about the cost that's behind this, right? So first you have to think about the cost of actually maintaining another data warehouse, which is a infrastructure level software, right? You have to maintain. It's stateful, uses a lot of resources. It's really difficult to maintain, right? And think about the cost of the data ingestion pipeline, right? Not one, for one table, but thousands, hundreds, thousands of tables, right? Maintaining those ingestion pipeline, running file from one format to another, right? That's really expensive. That use a lot of resources, really error prone too, right? And you have to think about, matching the schema, matching the data type, right? Matching the SQL, and doing a whole new set of schema design inside of your data warehouse for that storage engine, right? That's a lot of labor that's wasted there. And the most important thing is you're breaking the essential Apache Iceberg or the data lakehouse promise, which is a single source of truth data, right? For all of your workloads, right? So this is the biggest thing, right? You're sacrificing your whole data governance. The whole reason why you use Apache Iceberg in the first place, just to get better performance. And we don't think that's the way it should be. Okay, so how to make it faster, right? So first, let's look at some Apache Iceberg v3 features, actually one v3 feature that really gonna accelerate your query performance, right? And that feature is, it's just deletion vector, right? There are a lot of challenges with position delete, which was introduced in v2, right? Position delete is where you're storing all of the positions where the rows are deleted, positions of the rows that are deleted. So when you read, right, you merge all of the positions, right, into the query, right, and then so it's supposed to be a lot faster than let's say running equality deletes, but it has a lot of challenges, right? So it's granularity dilemma. So which one do I pick, right? So the delete files are oriented. They have two scopes. So first is either a partition scope. So a delete file can be responsible for all of the data files in that partition, right? Or it can be a file scope. So basically a deletion file for each one of the data files, right? But each one of them has a kind of like a trade-off, right? So for a partition scope deletion file, right? Because there's not really a one-to-one linkage between the deletion files and the data files in this way of deletion file orientation, right? So when you read, actually, you don't know which deletion file you need to read. So you actually have to scan through, open all of the small Parquet files and see which one you actually want, right? So you end up reading a lot more deletion files, if it's partition scope. But when it's file scoped, there's just a lot of deletion files, delete files, right? So it's either query over or query overread, or it's metadata explode, right? You have to pick either one, and that is a huge problem, right? For query performance. But if just reading too many files, you're just slow, right? Or you have too many files, it's slow as well, right? And second is when you write your deletion files, your writer actually have to do a global sort of the all of the data that's trying to write into it, right? So sort on the path and the position, right? So for every single delete file, you have to do that, right? So that's a big shuffle on the writer side. If you're using Spark, that's a really big shuffle there, right? It kills data locality, right? And it really slow down the update and delete process, right? And third is all of the manual, the minor compaction you have to run, right? With all of the delete files, if you don't really compact them on a regular basis, if they actually stack up too much, right? Table performance can degrade substantially, right? And finally, it's the problem with the Parquet file itself, right? Just too many files to open, right, and merge. And reading Parquet file by itself is expensive. Decompressing a Parquet file is expensive, and the records, the position records in the Parquet files, the reader basically have to read them row by row, right? And it's really slow. It's just not the way you do it, right? It introduces extra I/O because just the number of delete files you have to open, right? And really a lot of CPU pressure, for decompressing the Parquet files. It's just go over each one of the records, right? And that is really, really problematic as well, right? So how V3 solve those challenges, for granularity dilemma? right? So first it introduces a puffin file format, right? So it's a binary format, for the deletion vectors, right? So in each one of the puffin file, you have a bitmap that represents a bitmap blob that represents a data file, right? So you have many bitmap blobs inside of each puffin file. So right, so because of that, 1-to-1 ratio, right, is really precise and it's really compact. We're going to show some number later, right? And also we have a new manifest column that's called reference data file, right? So now we have a strong linkage between the data file and the delete file, right? So we make sure there's no overread, right? So we make sure there's no zero false positive there, right? And also because we were using bitmap, sorting is not a requirement anymore, right? So bitmap just have it have no ordering rules. So writer was just flush everything that's in memory, uh, uh, flush all of the rolling bitmaps that are in memory, and that's calling it a day, right? It's gonna work. And also uh bitmaps are a lot cheaper to maintain, right? Updating a bitmap blob is a lot cheaper than, let's say, rewriting a whole Parquet file, right? Um, so because that's so much cheaper, now we can do something like when you ingest, instead of leaving the compaction to the other day, right? Doing that asynchronously. And now the Iceberg spec actually mandates the merge of new existing deletion vectors at the query ingestion at the data ingestion time, right? So there is no more like manual minor compaction, delete file compaction uh, job that you have to run and maintain by yourself, right? Basically, to summarize, right? So deletion vectors are puffin files with uh, bitmap blobs, one for each data file, right? And there are many bitmap blobs in the Puffin file, right? And this is just way faster read, right? Because reading a bitmap, we can actually read it in parallel, right? We can actually vectorize read that thing, so it's a lot faster than actually unpacking a Parquet file and reading that off the chart, right? So this is basically how it works. And here are some benchmarks from when this feature was designed. That was in the Apache Iceberg design doc, right? So first is way faster. It's faster writes, right? Because you don't have to do that sorting, thing again. So it's around this much faster for writes, and it's way faster for reads because reading a bitmap blob off of a binary file, with no decompression. It's just way faster, right? Query engine can do this a lot easier than what it was done in V2, right? With the Parquet files, and better compression for random deletes, right? Rolling bitmap is really good, if your deletes are sparse, right? All over the place, right? Are sparse. So we see when the deletions are dense, not really much difference there, but when it's actually random, you can see a big difference between the two, right? So okay, so this is basically the one feature that is really gonna accelerate your query performance. If you want to learn more, we're gonna send the link to the design doc later. Okay, so how to accelerate Iceberg queries, right? So here are some like just the common tips and tricks, best practices of how to maintain your Iceberg tables for faster queries, right? Some of this you might already know, but just this is just an overview. Okay, so first, let's take a look at the challenges, of optimizing Iceberg table for fast queries, right? So first is small file exposure, right? So when you ingest your data into Apache Iceberg, right? Um, After ingestion, actually is not done, especially if the update interval is lower, right? You're trying to do real time, or Apache Iceberg cannot really do real time, but near real time kind of analytics, right? So very small batch of files in very small size per file, right? But when you accumulate those small files, it's actually really difficult for the reader scanner to efficiently read that many files, right? You have files that are just 1 MB, and you have a few million of them. It just doesn't work, right? And second, it's metadata blow, right? And that's together, with the deletes we talk about, right? With the V2s, you want to do your you want to keep your metadata small, right? Because if there are too many small metadata files, that can be a problem for the reader as well, right? You want to do those metadata rewrites. And then is partition skew and just poor data layout, right? So this is just like your typical, common data warehouse challenges. So how to optimize, right? So first, you have to know about the Iceberg features, right? Iceberg make it incredibly easy to do partitioning, right? So use those transformations like truncate and bucket, right? So using those, you don't really even have to specify, which column you're trying to prune on, right? As long as you're declaring that correctly, that can work automatically, right? So definitely use all of the Iceberg features that are available there, right? So managing your file size is very important as well, right? So target around in the ballpark of 100 megabytes to a gigabyte per file. That is the best, for really good query performance, right? So you want to regularly compact your small data files, your small data packet files, right? And also, if you have deletes, you want to optimize that as well, right? If you want faster reads, if you're still on V2, you would want to prefer position deletes over equality deletes. And you would want to compact, those delete files, doing minor compaction, search that up, in the Iceberg documentation, right? And also take a look at V3. I think V3, the spec was just released, in 1.8.0 or 2. I can't remember, but it should be there, right? Take a look and upgrade. And then is to control your metadata growth, right? So you want to rewrite your manifests pretty regularly, right? So you don't want too many small manifests, small metadata files, right? You want to expire your old snapshots regularly, right? You want to compact your delete files regularly too. We just talk about, right? And then you want to choose the right kind of storage format, right? So use something that's columnar for your OLAP queries, right? Not something in the row format, something like Apache Avro. That's a lot less optimal if you want to try to run high performance OLAP style like queries, right? And also, last in the end, your typical data warehousing tricks, they still apply, right? Things like sorting, right? Like partitioning, like doing indexes, right? Creating secondary indexes, and collect statistics for your query engines planner. All of those still apply. So use Apache Iceberg like it is a data warehouse, right? To optimize for your data warehouse performance, right? So we talk a lot about new features that make the engine faster, right? The queries faster, and we talk a lot about the best practices. What kind of tools you want to use, and what kind of maintenance you want to do on your Iceberg table to get better performance, right? But none of that really matter, if you are not really using the right engine for your workload, right? Um, you can have Apache Spark, that's really optimized for those long running batch like workloads. You can configure the hell out of it, to try to make it work for your low latency kind of workloads on Apache Iceberg. But you can probably make it work, but it's gonna probably not worth your time, right? So definitely, choose the right engine, right? Choose the right engine, for your workload really goes a long way, right? Query engines for data lakehouse are just not, a lot of them are not built for those like data warehouse like workloads, right? Some of them are more optimized for long running batch workloads, uh, not low latency, high concurrency workloads, something like Apache Spark, right? Or some of them are built to connect to a lot of different data sources instead of maximizing performance for what, right? Let's think about something like Trino, right? Trino is known for its really nice uh, stack of connectors, to all kinds of TP databases everywhere. You get okay performance for all of them, but not really maximizing performance for one single storage, right? Um, so here is when where StarRocks comes in, right? Um, okay, I think we have some questions here. Okay, let's take a look. Take a look at the questions again, right? So here entering StarRocks, right? StarRocks is a query agent built for data warehouse workloads. StarRocks and Apache Iceberg really creates a lakehouse, for your high concurrency and low latency queries, right? So first is a introduction of the StarRocks project. So it's Linux Foundation open source project, right? Apache license, open source, a few years ago, right? It is purposely built, for those data warehouse like workloads. It natively integrates not only with Apache Iceberg, but also with Delta Lake, with Apache Hudi and Apache Pymon, right? To create that kind of high concurrency, low latency kind of query experience on top of open and standardized file and table formats, right? It has a very simplified architecture with really no external dependencies, just FE for a metadata management to connect to your catalog service and read off your metadata, and do query planning and the CN nodes, to do data IO and also to perform, query execution, right? It has a just these are the two kinds of processes that are there. It has a really simple architecture, and it supports a standard SQL, and it also has a Trino dialect support as a switch you can turn on, right? So the performance of StarRocks is really great because it is actually a query engine that is optimized, for data warehouse like workloads. We're going to go into some of the features and innovation that is done, in the next few slides. But first, let's take a look at performance. So this is TPCDS 1 TB, StarRocks versus Trino, right? So this is more of your more complex joins with high cardinality, multi-table joins with high cardinality aggregations, right? So StarRocks is around 4.5 times, faster than Trino on TPCDS 1 TB. So where is it getting all of this performance from, right? So we're going to talk about that in the next few slides. So first, let's talk about some of the common challenges of on the engine side, reading off a Apache Iceberg table, right? So first, parsing the Apache Iceberg metadata can be really an expensive process, right? So you basically read from the catalog and you read and parse the metadata file, and you read and parse the manifest list, and you read and parse the manifest file, right? So the cost can come from, really high IO latency while reading the files, right? Actually getting the files from S3 to the engine itself, use a lot of IO, right? And CPU pressure when parsing the files, parsing all sorts of files in the Apache Iceberg metadata tree of metadata, right? All the delete files, all of the Avro files, you have to, parse them and use a lot of CPU, right? And also handling delete files, we talked about before, the V2 delete files, it's can be a big challenge too, right? So metadata latency can actually be the bottleneck for a lot of the OLAP queries, before you actually know it, right? A lot of the queries are execution heavy, CPU heavy, but a metadata latency can actually be the bottleneck because it's a really difficult problem to solve, right? And fetching data file can be a challenge here as well, right? So first is also, the network overhead that's above it, right? So each query scan can return, gigabytes, tens of hundreds of gigabytes of data pretty regularly, right? So the IO overhead there is quite high, right? And you have to consider the slow performance of your data lake storage, something like S3, right? It's really good durability, but the latency of S3 can be 100 to 200 milliseconds, which for a big query scan, multiple S3 reads, that latency just not acceptable, if you want your latency, query latency to be lower, right? And also, if your Apache Iceberg tables are really not optimized, too many small files lying around, right? It can be very unoptimized, for query performance that way. Okay, so how StarRocks accelerates data lake query performance, right? So first, it has a data metadata cache, right? Automatic caching framework, hierarchical caching format is based on both memory and disk, to overcome the low performance of data lake storage systems, and also to address, the metadata retrieval challenge, right? And to save I/O costs from actually fetching data from the external storage, right? Both metadata and data from S3, right? This is the first. And second, it has an MPPU architecture with in-memory or between nodes memory data shuffling, right? So it supports high cardinality aggregations, multi-phase aggregations, and shuffle joins, right? But everything is done in memory, right? So it's really optimized for low latency kind of workloads on complex queries with high cardinality aggregations and multi-table joins, right? So MPP is what you want to look for. And also system level optimizations, right? StarRocks was built just to tackle data warehouse like workloads, right? So performance is always the most important aspect, when like during the design of the system, right? So it's implemented in C++. The execution layer, the one that actually doing the query execution, is implemented in C++ to fully utilize, SIMD instruction sets, and also all of the operators inside of StarRocks are, are vectorized. So basically, we process everything in memory, right? We do that everything by column, by batch, right? With SIMD, and this is what this is basically a must-have, if you want really good OLAP performance, right? So with the right optimization, getting data warehouse performance on the Lakehouse is not only possible, it's actually quite easy to do, right? Um, StarRocks is an open source query engine, but before, just a few years before, it was a data warehouse. It actually has its own storage engine, right? Then here we're gonna do a comparison, between a Lakehouse architecture and the data warehouse architecture, right? So on the left is StarRocks as a data warehouse. It has its own storage engine, right? And same thing too, cloud object storage, right? Uses S3 to persist the data, right? But the key difference here is powered by StarRock's own storage engine instead of Apache Iceberg plus Parquet files, right? So it's storing everything in StarRock's own table format, and storing everything in StarRock's own optimized file format, right? And on the right is StarRock's own kind of like an open lakehouse architecture, right? Instead of using its own storage engine, it's using Apache Iceberg like table formats and open file formats such as Parquet ORC, right? To swap out, the star storage engine. And let's see the difference of performance, and between the two, right? So first, let's set a baseline here, right? StarRocks as a data warehouse is incredibly performant, right? StarRocks versus ClickHouse versus Apache Druid out of box here. This on the SSB 100 gigabytes performance benchmark. So this benchmark is a lot simpler than TPCDS, right? So this more resembles your customer facing kind of workloads, right? So it's multi-table, but only one table that's really big. So every join are a bigger table join a smaller table, right? And the aggregations are a lot easier to do, right? Most of them are lower cardinality, right? And the query itself is just a lot simpler, a lot more structured, than those TPCDS queries, right? So on the right, you can see everything has a flat here. It's actually a variant of the SSB benchmark test, done by the ClickHouse folks. So basically, it's a denormalization of the original SSB benchmark test, right? So instead of doing all of the joins and aggregations on the fly, the flat version only does the aggregations on the fly, but not the joins. And StarRocks multi-table is StarRocks running on the original SSB benchmark test, so meaning you're running the aggregations and the joins on the fly together, right? So here, let's see the benchmark results, right? So StarRocks flat, uh, among all of the flats, StarRocks is the fastest. It's way faster than Apache Druid. It's faster than ClickHouse. But StarRocks multi-table performance is actually faster than Druid's single-table performance, basically running the joins for free, right? But join is probably the most expensive thing you can do, with the SQL query. So this basically shows the baseline, right? StarRocks as a data warehouse is incredibly performant, right? And here is the difference between data warehouse and a data lakehouse, right? So StarRocks as a data warehouse versus StarRocks as a query engine. And this is actually on top of Apache Hive. Um, Data warehouse persisted, and for the data warehouse setup, the data actually persisted in local disk to maximize performance, right? Hot queries between the two, same exact hardware, TBCDS 1 TB. The data warehouse solution is only 12% faster. So think about that. You're just giving up 12% of the performance. What do you get back? Single source of truth on your data lake, right? You only manage one copy of the data. You get all of the benefits, all of the data governance benefit, that's promised by a data lake house, right? So here's the difference there. And beyond just fast queries, right? There are actually challenges with ETL workloads that we see too, right? Just imagine that you are a data engineer, right? That you are using a query engine and let's say some kind of storage, right? And using Spark to do all of your data transformations, right? And one day your team gets back and says, there's a slow query you have to solve, right? And you identify a slow query. And after some analysis, you figure out the only way to solve that slow query is actually through a pre-computation pipeline, right? So you probably you pre-join few tables into a denormalized table, right? But that whole thing is not going to take into effect, until you rewrite the SQL or you redo your application to point to the new tables, right? It actually forces engineer to figure out all of the data pipelines before developing the client-side application, because that rewriting process is too much of a pain, right? So they end up doing that beforehand and building pipelines to generate tables that might never get used, right? It really lengthen your development cycle. So StarRocks actually solved this by Materialized view, right? Materialized view, yes, it can do a lot of things, right? Single table, multi-table, right? And incremental refresh and those partition level incremental refresh. But the key of StarRocks Materialized view is its query rewrite capability, right? So you don't have to change your SQL scripts with when you are trying to do a pre-computation pipeline. It simplifies the query process. So basically how it works is that when you send out a query, StarRocks cost-based optimizer can directly, automatically route your query to the most appropriate materialized view, so you don't have to change your SQL script, right? It really simplifies the query process, so you don't have to, plan your pre-computation pipelines beforehand, right? So you have the flexibility of actually configuring your pre-computation on demand instead of doing that all beforehand. So you end up going production a lot faster. Okay, so here is all about StarRocks, a higher level overview of StarRocks. And here let's talk about some use cases, right? This is actually a use case that was presented in the Apache Iceberg Summit 2025, just a month ago, right? TRM Labs is a blockchain company. It keeps your blockchain data secure, right? So they're using they do customer facing analytics, right? Their data size is around 100 terabytes and growing around 25 to 45% annually, right? And their query profile is really complex with joins and high cardinality aggregations. And they have a 3-second P95 SLA for their customer facing workloads, right? And they need to deploy this for multiple of their sites on prem, right? Before they were using a BigQuery as the storage as well as the compute, right? But they were soon running into performance bottlenecks, right, on GCP. And then they considered other kind of solutions, right? And they end up unifying all of the data on Apache Iceberg, right? And they considered different compute or query engine options. They considered Trino, StarRocks, and DuckDB, and they benchmarked on just pure filtering performance and complex joins and aggregation performance. And they end up going with StarRocks, right? Using StarRocks to swap off the compute layer, and using Apache Iceberg for the storage layer, right? So they see a 50% improvements in their P95 performance and a 54% reduction, in query timeout errors, right? And you can read about this later. I'll send out a blog later to you guys and read about this case study. And there are more, way more, StarRocks and Apache Iceberg use cases, right? So first is another customer-facing like workloads, right? So this is actually a SaaS for farmers, right? For their livestock like cows, and to monitor their well-being, right? And they were doing that on Apache Iceberg and Athena, right? And they figured, Athena was really not the right tool for customer-facing analytics. And then they moved to StarRocks and they dropped their latency from 2 to 5 minutes to around 700 milliseconds to 1.5 milliseconds. And they unified their data on a single source of truth, powered by Apache Iceberg, right? And the second is Rednode, and this was a presentation as well, Apache Iceberg Summit 2025, right? So they have around 100 petabytes of history of data. It's just stupid amount of data, right? And they add around 3 petabytes of data every day, right? And they were using StarRocks, and they are using StarRocks and Apache Iceberg, right? They're able to get better than ClickHouse performance directly on Apache Iceberg with StarRocks. And lastly, not last but not least, is Tencent Games, right? They actually presented this work in the Apache Iceberg Summit 2024, right? So they united petabytes of their originally siloed data scattered in different TP and OLAP systems into Apache Iceberg. They built a PB scale Apache Iceberg Lakehouse, with just 10 seconds of data freshness, actual real-time analytics. So this is actually all I have. So StarRocks and Apache Iceberg, explore, and please join the Slack channel if you haven't. And now let's take a look at some questions. First, does StarRocks have any kind of write-back cache? Oh, I think I already answered this. This is the cache warm-up. Yes. So you're able to warm up the cache of a table, before you actually run any real queries first. Timeline for V3 inclusion once V3 is mastered into Iceberg. Oh yeah, we're still discussing this. we're still discussing this. But yes, we're looking to support um, most of the V3 features that are there, especially role lineage and for deletion vector. Definitely, we're looking into the implementation. Do you have benchmark comparing StarRocks to Snowflake on Apache Iceberg? I don't think we have any out there publicly. But I'll talk to the team if we can have pull something together. What kind of performance difference one expect from native storage S3 with compute nodes versus Iceberg? Okay, so if you're just running benchmarks, I believe it's quite similar, right? But it's really case by case. So um, there's still some cases that it might not run as fast. So, for example, um, uh, low cardinality is a big optimization we did, with the native table. And we did that 3-4 years ago, with our own storage engine. And we just released our new implementation for Apache Iceberg, low cardinality uh, acceleration, basically optimization, right? But the performance can really vary. It's sometimes it's not working as intended, right? But we're still solving those edge cases as we see them, right? And also statistics. We're building uh, uh, statistic collection on top of Apache Iceberg to match, what we have, with the internal table, right? But there's still times, where just a column just would not prune, right? So it's really a case by case discussion, right? You have to try it out for your own use case to be able to see, right? Actual difference. I'd really like to know if there's any additional latency with S3 versus native storage for recent added data. If I'm trying to do data from the past 24 hours, will that be automatically added to local node cache where I have to fetch from S3 on the first query? Yes. So yeah, you can do a warm up. That's always gonna work, right? If you don't do a warm up, and yes, it will need to be you're gonna see a slow first query. So yeah, so it depends on your use case. If you use a warm up, this will not happen. Yes, it will be recorded. If I need to update the Iceberg table from Spark or other query agent, the StarRocks auto pick up the latest update. Yes. So, um, um, yes. So we read the version number, so we know like which if the data is outdated, so we automatically updates the metadata. So yes, we have a problem with the quality file where decides wait, we have a problem with equality delete files when Iceberg decides which equality files to consider for data files. It checks by minmax. Yes. We have small equality delete files like 5 to 10K, but have to check a lot of data files against them during query. Yes. Wait, this is a long question. We'd like StarRocks to do Bloom filter or auto optimization for equality deletion file elimination. Yeah, let's talk offline. Let me see. Yes, I'll reach out. I'll reach out to you with our team and we can discuss this further. There. Thank you, Robert. And we have more questions here. Let's see. Besides caching, you have to know this query over Iceberg tables, indexing. Like, yes, we actually have so many things we built for Iceberg, like the V2 deletion file problem. We actually have a workaround for that, so you don't read as many delete files for position deletes. And we have like your metadata, right? You have a lot of metadata files. We actually figure out a way to read all of the metadata files in parallel with our CN nodes. So basically to MPP the metadata fetching process. That and also like we were able to cache not only the metadata but also we cache the deserialized Avro files, right? And that's a huge cost away too. We have many optimizations that are done to Apache Iceberg, and we actually have a talk there. I think you can check it out. So if you go to Apache Iceberg's website, and there is a video session. I think it's a video section. Let me take a look. Oh, this is a spec. Talks. Um, and you search for this optimizing query performance for Apache Iceberg at scale. This is done by one of the StarRocks committers. This outlines all of the performance. Probably not all by now, but most of the performance improvements, optimizations we did specifically for Apache Iceberg. Right, a lot of cool things there. when is the planned release of V3 support for cellular data StarRocks? We're still discussing that. Hopefully, we can have some news um, sometime next month. Hopefully, we'll be at the upcoming Iceberg meetups in Seattle and the Bay Area. Yes, yes, I will. Hope I see you guys there too. So if you have a cool iceberg story, you can talk to me. Maybe we can get you on stage. There is one on May the 6th. Maybe it's a little too late now. Today's the last day for submitting a CFP. And there's another one in the Bay Area, um, East Palo Alto AWS's office. Um, that's May the 16th. So you have a cool topic. Make sure you know. Okay, I think this is all of the question. Thank you guys for joining. Thank you. See you guys again next time. Thank you.